Alright, question 5, we have Alex producing images and sound effects for a website. We have part of a bitmap image shown here, and the letters represent the colour as shown here, so white, white, red, red, so on. We have to use the example in figure 2, which is really important, so that means we're going to have to talk about it, we can't avoid it. Explain how a bitmap image is stored on a computer. So, using an example is going to be at least 1 mark, and the explanation will be probably the other 2 marks. So, let me get rid of this, it's going to be annoying. Okay, so bitmap is stored, bitmap consists of pixels, so pixels is kind of like the smallest unit of a photo, a picture, so this would be a pixel. And so bitmap consists of pixels. You then have each pixel being a set colour, so white or blue or light grey, I'm guessing that is, yep, light green even. And then each colour has got its own binary value, and that'll be how it's stored in binary, obviously, because it's in a computer. So let's write this down, and we're going to have to do an example as well. So a bitmap image consists of pixels. Each of which has a set colour, or just has a colour. The colour will have a corresponding binary number, and then we've got to do an example. So, I mean, we can say like W or white. Oh, let's just do e.g. W white equals 0, 0, 0 in binary, and that should be sufficient. That should be a sufficient example to kind of prove we understand it. 4b, we have to explain how reducing the number of colours in an image can reduce its file size. So if you have less colours, let's take an extreme example, and let's say that our bitmap was black and white. Only 2 colours. We only need 2 options, 0 or 1. So we only have 1 bit basically. This would be called for colour depth or bit depth, just 1 or 0. Whereas if we have many colours, we have to increase our number, of bits per colour. So so less colours means less bits per colour are needed, or less bits are needed to represent 1 colour. But that means the same thing. Are needed, which implies less bits per pixel. I wouldn't recommend you write it this way, which equals a smaller file size, because you're like if it was black and white and it's stored in a file, like, you know, this would be white, black, 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 white, black, black, and this would be our first row, and that's how it's stored in binary. So obviously I don't know, hopefully this makes sense. I can't think of another way to explain it. Right, the final image file may contain metadata. Describe, use an example. They're hot on the examples here. What is meant by metadata for 2 marks. So relatively simple if you know what metadata is, obviously. So metadata is data about data. So it's stored alongside your, raw data with extra stuff. It's often used to help format it, for example, or just to help you. Like if you take a photo using a fancy SLR camera, it will save a model name and things like, I don't know, the exposure or whatever. So it just contains data about data. But yeah, so metadata stores information. Okay, that's not gone well. That's me pressing the button down on my tablet. Metadata stores information about the image or about the data, and then we've got to do an example again. When it says use an example, you have to do it, you can't just avoid it. E.g. the width of the photo, that would be sufficient. Oh, height, colour depth, I said exposure, aperture, and so on. I realise I forgot about, there we are. Alright, so he's creating a audio recording of himself playing the guitar. and we've got to explain how sampling is used to make the recording. So the way sampling works is if you have an audio wave like this, which for guitar I'm sure looks nothing like, we have time and we have, I guess, displacement up here. Sampling works by recording at regular intervals the height of the wave, which is also called the amplitude. So it's always set intervals. This is meant to be equal distance across, and then, like I say, the amplitude is measured, so the height of the wave is measured, and whatever values here on this axis will be translated into binary and stored that way. So at regular intervals, the amplitude is measured. At regular time intervals, let's say, the amplitude is measured, and then the value of the amplitude or the height is then stored in binary. The value of this is stored in binary. And that's what sampling is. So continuing with sampling, we are asked about the effect of increasing the sample rate of a recording. So the sample rate is how often a sample is taken, so how often these intervals are, they're always regular, but how often. So say if, instead it took it twice as often, that means you're going to have twice as much data. So the effect is the audio will be more, the representation you have will be more true to the original sound, but the file size will increase. Okay, so I forgot to speak. You wouldn't think that looking at how bad the handwriting is. I was actually trying to concentrate on it. So I've said as like a two-parter, the digital representation is more true to the original analog signal. I'll explain that in a sec. And then more data is stored, so the file size increases. So you've got to be a little bit careful. I would always avoid saying things like, oh, it will sound better, because that's not totally... It's probably true, but other factors involved. Like if you are playing it through an awful speaker, it won't sound better to you just because the sample rate's increased. But it does mean the representation is more true to the original signal. So this is an analog, an original acoustic guitar, or whatever it is. Whereas, you're creating digital representation because it's in binary, which your computer needs in order to use. So it's more true to it. It doesn't necessarily mean it will sound better. That's kind of your perception of it rather than, a clear cut. This is always true. So I'd be a little bit careful when talking about things like quality because that's, your own opinion in a way. But the file size is definitely always the case. For question 6, we're given a computer specification and we have to describe benefits of a dual core processor over a single core. So dual core means you've got 2 cores. Hopefully that's understood. And it means you can perform, or it will support something called multitasking, where it can basically process 2 tasks at the same time. So supports multitasking. So two tasks, 2 instructions can be executed at the same time. So the effect of this is overall processing is done faster. It probably doesn't matter to the example, but supports is a little bit of an important word, because just because you have 2 cores doesn't mean every process, every program is designed to utilize dual cores. People buy really expensive processors with tons of cores and they'll use software that never utilizes it because it's not really designed to. So you do need software that's designed to be split up like this. We then need to describe 2 differences between RAM and ROM. RAM stands for random access memory and is where the instructions are moved to when they're going to be in preparation for execution. So they're moved when you open a program, they'll get moved from the hard drive to RAM. ROM stores things like boot up instructions, really fundamental things which are never going to be changed, because ROM stands for read-only memory. And so first of all, when you turn your computer off, everything on the RAM is wiped, whereas on ROM it's persistent, it stays there. And this means, or the technical word for this is volatility. Let's change colour. So RAM is volatile, which means as soon as you turn power off, the data is lost, whereas ROM is non-volatile. It's an easy 2 mark, especially because they're kind of like the converse. The second difference, we can say that ROM, hence the name, read-only memory, cannot be changed, or yeah, let's just say cannot be changed. You can actually change some ROM, but with difficulty. ROM cannot be changed, whereas RAM can. And that should be sufficient for 4 marks. You've got to be a little bit careful with kind of doing converse points, like just the opposite, but I think this should be okay. So a very standard question here. We're told that he's upgrading the RAM on his computer. Explain why this would improve the performance. So it goes back to what RAM does, which is to store the currently open application data. And so having more capacity for this means you can store more instructions in RAM. RAM is used because it's a lot faster than other memory types like a hard disk, and so you don't have to use the hard disk, which is slower. When you run out of RAM, part of the hard drive is allocated to kind of it's called virtual memory, and it will it'll be really obvious if you've got tons of programs open at one time and you go back to use a program you haven't used for maybe a few hours, and it's a lot slower to open and to kind of work. It means because probably you've used up your whole RAM capacity with all the other applications you've got open, and it's using the slower hard drive to access or to store the program data. So the more capacity you've got in your RAM, the less likely it is that the hard drive will have to get used for virtual memory. We have another QWC 6 marker here. You're likely to get a couple in your exam, so you just kind of got to accept that, unfortunately. This one's really easy though. It's about upgrading hardware and how that would improve performance. So for some of you this would be incredibly easy, and I wouldn't assume that this won't come up at all. You're not going to get an exact same question in your paper, unfortunately, but often they'll split this up. This is quite a common way to test your knowledge of hardware. They'll say we've already looked at how will increasing for RAM affect the performance. They often will ask how will the clock speed of the CPU affect performance. Again, I'm not going to write this out because I might lose the will to live on this tablet. So clock speed is essentially how fast the CPU is operating. So the CPU is synchronized by this clock. This clock is like a metronome that kind of sends pulses out and synchronizes the CPU. So this is cycles per second. It's measured in hertz, which is a unit per second. And this is how many fetch, decode, execute cycles happen per second. And so obviously if you increase the clock speed, more of these cycles happen per second, more instructions get executed per second, and so it's going to be faster, so you'd kind of have to explain that. So again, there are loads of things you could talk about. Another one would be, cores, but we've already kind of looked at that. You could talk about it again, but let's assume we're not going to. So you could also talk about increasing cache, or the size of the cache. And cache is very small, fast memory that exists very close to the CPU, if not in it, as in physically it's very close. It's also very fast. So cache is there to store instructions that are frequently accessed. So having more of it means you can store more data that's frequently accessed, store more data, and so because the cache is faster than for memory, you can store more data, and so this will be done. More data is able to be accessed quicker. A third one, which is slightly less obvious maybe, is installing an SSD. An SSD is a type of secondary storage. It's very fast. It's flash storage, and so often people will replace their hard disk drive, a mechanical one, which is quite slow, with an SSD, which is pretty expensive. But it's a lot faster, and so this would make things like if you store your operating system on the SSD, it makes booting up a lot faster. Because it accesses and stores data faster. So none of these points are very coherent. So the challenge would be to kind of convert these into a acceptable answer. So really, I think probably 3 points is sufficient for this. If you're going, as I explained earlier, it's not marked literally like this, but if you're going for kind of like a mark for identifying it and then a mark for an explanation. It's going to be quite a detailed explanation, so it's going to be very kind of logical. So clock speed, if you increase the clock speed of a processor, it means the overall performance will be faster because more cycles per second, more instructions executed per second, and so on. So it's going to be quite a logical chain of logic, and so you need quite a detailed explanation for the top band. But maybe in your plan or in your head you'll be going, okay, I can talk about clock speed, cache, SSD, and then you can kind of form your answer in your head as kind of like a rough plan, maybe like half a second for half a minute or a minute, and then you'll write quite a coherent answer in theory. For 7a, we have to identify two differences between a WAN and a LAN. So a WAN is a wide area network and a LAN is a local area network. So the first difference is the most obvious in that their geographical area is different. So a WAN is over a wide geographical area, whereas a local area network is over a smaller geographical area, like a school or an office or a building, whereas a WAN would be something like the internet, perhaps. So WAN is over a larger geographical area. The second difference is slightly less obvious, but WANs use external infrastructure, like let me try and spell this, infrastructure, like using, let's do e.g. routers. So the internet uses routers from all over the world, satellites, etc. So a WAN uses kind of this external hardware or infrastructure, whereas a LAN uses its own hardware, so its own cables, its own really, because it's over such a small distance, it's not using infrastructure that's already in place, it's using infrastructure there for the purpose of the LAN, whereas a WAN uses hardware that's there for other LANs, because really a WAN is built up of loads of LANs, and basically it's using the hardware from the LANs in order to create the wide area network. So that's what this second difference is. For part B, we have another kind of two-pronged answer, except it's worth twice as many marks. We've got 4 marks versus 2 from a previous question. So we have to describe 2 benefits of using a client-server network instead of a peer-to-peer network, and it's for this OCR supermarkets example company, and it's about connecting checkout computers to the store's server. So this is definitely more suitable for a client-server network, where you have your clients, which are the computers, and the server, which is the server, believe it or not. And then you have the alternative, which is a peer-to-peer network, where actually the nodes are all kind of communicating between themselves directly instead of going through the central server. So this wouldn't be very suitable for this company, because having a client-server network allows you to connect the computers to the store's server. So data can be stored centrally. You get your first mark for kind of identifying this, so then you've got to explain it, because it says to describe. Data can be stored centrally, so data can be controlled. There's an element of security there, and accessed by any stores or anyone's computer, and accessed by any employee's computer. Another benefit, looking at the context, is allowing you to back up data centrally. So data can be backed up centrally. If everything's stored, dear. You can tell I'm recording this very late at night. Backed up centrally. It can be backed up centrally because everything's stored there. It doesn't need to be backed up on individual computers. So we're essentially getting 1 mark for identifying it, and then another mark for actually kind of the explanation of it. Part C is a question that comes up a lot, both at A-level and GCSE, and by different examples, because obviously students don't really understand the difference, which is obviously a failing of teachers and textbook writers and people like me, because I imagine most people on the street don't really know what the difference is between the internet and the World Wide Web, but as a computer science student, you'd hope you would. So the World Wide Web is for web pages, connected web pages with hyperlinks, whereas the internet is actually the hardware, so the servers and the network of networks. And so basically the web pages are stored on the servers, and that's the difference. So the World Wide Web is web pages or connected web pages, whereas the internet is actually the kind of network infrastructure, so the hardware, and web pages are stored on the hardware, i.e. the servers. You'll notice that I've given up trying to write this out, but that's the difference, and hopefully you just gotta, if you're confused, you just gotta draw this into your head. So World Wide Web, HTML, things like that, CSS, whereas the internet's things like the servers and the actual infrastructure, so the cables and the networks connected together, but they host the web pages, which is the World Wide Web. We're kind of going full circle with question 8 because we're going back to binary and decimal like we did in the first question, so we're doing a bit more converting. We are, for just 1 mark, it's never worth that many marks. We're going from 191 in denary or decimal to binary. So I always do this using a table method. You can also use the algorithm method if you're more familiar. Do whatever you want. You don't get a working mark, unfortunately, just get the answer mark. So I'm going to do a table, and we start off with, it's going to be a byte, so we start off with 128 as our first heading, 64, 32, 16, 8, 4, 2, 1, and that's our 8 columns. That's straighter than I thought. And we're going to do an actual lines, and now we can actually start the conversion process. So first of all, what we do when this is our kind of target number, we go how many times does the most far left column go into, the most significant bit, as it's also known. 128 goes into 191 once, and to find the remainder you'll have a calculator probably, but I don't, and I don't trust my mental maths. So 63 is our next sort of target number. This is our remainder. 64 doesn't go into 63, it's too big, but 32 does go into 63 obviously, and remainder 31. 16 goes into 31 once, remainder 15. 8 goes into 15 once, remainder 7. 4 goes into 7 once, remainder 3, and then we can actually fill it in that way. So this is our answer in red, so we can just write it out here if we want to. 1 0 1 1 1 1 1 1 in base 2. And just to check, it's an 8-bit binary number. We've got 1 2 3 4 5 6 7 8, and we're good to go. For B, we have to perform this binary addition for 2 marks this time, being particularly generous. So we usually do this 1 mark per nibble, as in 4 bits each. So we start off from the right hand side, and this works like normal addition if you're doing it in base 10, if you're doing this kind of table format, I forget what it's called. Anyway, so you have certain rules with addition because it's going to overflow. So when you have 2 1s, you write down a 0 and carry a 1. Now when you have 3 1s, you write down a 1 and carry a 1. The reason this is you kind of collapse them. So 1 plus 1 is 0, carry a 1, and then you have 0 plus 1 is 1. So that's kind of where that comes from. But if you can learn that 3 1s equals 1, carry a 1, and 2 1s is 0, carry a 1, it'll be good to go. Then we have 1 plus 0 is just going to be 1. 1 plus 1 is 0, carry 1, again 0, carry 1, again 0, carry 1, and then 1, 1, 1, and that's our answer. As usual, the final question is a dreaded 6 marker where you have to write an algorithm. I imagine for most people this will be pretty dreaded. So the kind of thing I'd quite not enjoy, but I could do outside of the exam conditions, but it is a little bit stressful, I think, if you're doing this in exam conditions. So you want to give yourself as much time as possible to do this question. You almost want to rush through some of the easier questions, like for little, really simple stuff you can do here. For most people this would be simple. You can kind of save 3 minutes if you're doing a minute a mark to kind of free up a bit more time to do this question, because it can be tricky. Sometimes it will be super easy. I don't know how hard this one is. We'll see. So for context, it's a memory game where you have 3 players have to choose between 0 and 100. If a number has already been chosen, a message is displayed as taken. If it's not already been chosen, the player's letter is placed next to it, and the quantity of numbers that have not yet been chosen is displayed. And I guess because it's tested memory, the winner is the one who has chosen most unique numbers, and they're stored in an array called numbers. A number that has not yet been chosen is stored as an empty string, and the players are represented by A, B and C. Okay, and we're shown an extract from the array, so we have our numbers 0 to 100, obviously skipping them out, and you can see, I guess, at a certain state in the game how it might work. So at the second position in the array, which would be 1, because we're doing a 0 indexing, C has been written, and yeah, I imagine, if I haven't misread it, that this would be essentially a blank string. Is that right? It means would be you know, strings of A, B and C in. So I assume that's what's going on. Hopefully I haven't misunderstood it straight away. So we've been asked to program part of a game. We have to write an algorithm for player A's turn, which takes an input, as an input the number that player A chooses, so from 0 to 100. If it's not already been chosen, stores an A in that array element. If it has already been chosen, outputs taken, counts and outputs for the quantity of numbers left that have not been chosen. So first of all, we're going to want to do our input. We don't have to worry about the rest of it yet. So So this is going to be in pseudocode, I think. You can probably write it in program code if you wanted to, but the syntax isn't going to matter so much. It's more your kind of logic of the algorithm. Don't do a flowchart; it wouldn't be appropriate here, or ever really in for OCR. So we need to do input. I'm going to do it in capital. It tends to be how you do it in pseudocode. So what we're going to call our variable doesn't really matter, but let's choose num chosen. I'm doing camel case. Okay, so we need to address the second point about if it's not already been chosen, it will store an A in that array element. So essentially, let's say the number chosen was 4 because we've got it here. So the number chosen was 4, and this is in the 5th position in the array. And previously, assuming this was an empty string before, i.e. it hadn't been chosen, then the program kind of has an if statement to say, okay, so I'm thinking aloud here, but we'll do if, what's it called, numbers, if numbers, num chosen to index it. Oh, good. Numbers chosen equals empty, as in no players got there first. We're going to, what we're going to do, we're going to write numbers. It's a bit repetitive. Numbers. I wish I'd chosen a shorter variable name now. Chosen equals A, and we can end if at that point. So actually we can't put end if here because the next point is to, if it has already been chosen, it will output taken. So you need to do an else statement. Let's shift this down a little bit. So we've got room for else. So else, in any other case, if anything else is in this position of the array, it'll be a letter, ideally. Else output taken. So we've addressed the first couple of points, the first 3 points actually, the first 3 bullets here, with what is relatively simple code. I'm going to change colour because I think red's a little bit much. So the final point is a little bit harder because we have to count and output the quantity of numbers left that have not been chosen. So really what we need to do, we need to loop through this array and match or to check basically every location in the array to see if it's empty. And when it finds one which is empty, like 100, it's going to update a variable. This would be the most simple way I could think of doing it. So a variable will be updated every time it comes across an empty string when it checks in each box of the array. So we're going to do a loop here. It doesn't really matter which loop you use. I'm going to use a for. Let's go on to the next page. I'm going to use a for loop because we know how many times it's going to loop. So let's use a variable because we need to use a variable in our index. Let's use I. I is usually used, doesn't actually matter. For I equals, we're starting from 0 to 100. We need to do an if statement again. If numbers I, so we're checking each box because this I is going up every time it loops. If numbers I equals empty, so I'm losing track of myself a little bit. This happens when you're trying to solve it for the first time. So we've got we're checking every box to see if it's empty, and we need to actually have data variable which we haven't initialized yet. We can do it here because we've got a bit of space. Let's call it count. It doesn't actually matter. Let's just set it to 0 to start off with. And when we do have the empty string in this box, we're gonna update count. Count equals count plus 1. That's meant to be an equal sign, and then we can end if and end for, and then output count, and that is our algorithm complete. I don't know where this stands in terms of difficulty. Maybe you can let me know, but hopefully you can see how I kind of approached it. You can see that, you know, I made a mistake in that I forgot to do the variable. You kind of learn how to solve it as you solve it. You need to kind of just jump in, make sure you understand this to the best of your ability. It wouldn't be the end of the world if you didn't understand it completely, because really the top bit doesn't matter so much for the actual context. It's more of a bullet points. They always seem to give you bullet points to give you a bit of a head start, or a bit of a way to approach it. And it's tricky, but you know, 6 marks isn't the end of the world. If you don't get all 6 marks, just do your best. Try and give yourself as much time. If you have 2 minutes to do this question, you're not going to be able to do it. So you want to be going to that exam with you're clearing in mind that you're going to leave yourself enough time. You might even want to skip questions to get to this. You might even want to do this question first. I don't know, it might demoralise you before you begin with the rest of the paper. But yeah, hopefully this video has been useful, and good luck with your exam.